Alright, so hopefully you just finished watching this cat video, the Smart Everyday video. I do think it's a little bit confusing. I'm not saying I'll do a better job explaining it than him, but I'm going to try and kind of break it down into more of what we've been learning and putting it into those contexts. So we're really looking at momentum. So what I want to do first is kind of look at our old school way of looking at momentum, and mainly this like collision, because in this case this is one of our cases where we said, okay, we're going to start with no momentum, and then we're going to end with no momentum. So we're really looking at this conservation of momentum where our starting momentum is just 0. So in this case, in order to conserve momentum, what we had was a cart moving in the negative direction and a cart that moved away in the positive direction. So in this case, we don't know anything about their masses, but we would say, okay, well, we have this negative mass going to the left, plus this mass going to the right, and those would cancel each other out and would be 0. So that's kind of our linear case, and it's really the closest analog that we have to what's going on with the cats, but the cats is a little bit more complicated. It's a little bit more confusing. So what we want to do is when we're looking at this cat, we kind of want to split it into two pieces. So he said in the video, this cat like arcs its back, and oh no, I only gave the cat one arm. Ah. Um, so when we start off with the cat, we don't have any angular momentum. This cat isn't rotating. So it's kind of in this situation, we started off, we had no momentum. So in this case, we start off with no angular momentum. And this just gets a little bit more confusing because before with the carts, we weren't changing anything about the mass of our carts. We weren't changing anything about the structure of those carts. We could have, but that situation looks kind of weird, and then we have outside forces, and that's odd. So what's weird and more complicated about angular momentum is we're able to change up that I component. We said L equals I times omega. So before we could really only change up something about our mass or our velocity. Now we can change stuff about the individual pieces of our rotational inertia by changing how that mass is distributed. So when we start off, we say, okay, we have no angular momentum. We're going to say that our initial, I'm going to point with the yellow, I don't know why. Our initial angular momentum is just 0 because our object is not rotating. So the angular momentum for the front half of the cat, which we're going to show in red, is equal to 0. And the angular momentum for the back half of the cat, which I'm going to show in blue, is also 0. So we start off, yeah, it's got some sort of rotational inertia, but because we have no rotational velocity, we have 0 total angular momentum for the cat. Then we're going to look at this next situation. He said in the video that the cat kind of pulls the ice skater trick, and this is what we were just looking at. This idea that, hey, if we bring our arms in, or if we bring our mass closer, then our rotational inertia goes down. But kind of internally, we're saying, oh, well, our angular momentum has to be conserved. So before it's got some sort of rotational inertia and a little bit of the angular velocity, but now it has to be conserved. So if we decrease our rotational inertia, our rotational velocity has to go up. So the cat brings its paws in and it's able to get a good amount of rotation. It's able to spin quite a bit in order to make sure that that half is starting to face downwards. And then in the back half, we're saying, okay, well, it's going to stick its paws out. So it has this larger rotational inertia because it kind of moved that mass further away from its body, this axis of rotation, and that made our angular velocity decrease. So we have this conservation within the front half and the back half, and then what we really need also is this total conservation. So in this case, we have a low rotational inertia for the front half, a large angular velocity, and then a large rotational inertia for the back half, and then a low angular velocity, and they're happening in opposite directions. So we have, just like we saw before, something moving in the positive direction, something moving in the negative direction. So I only have 30 seconds on this, so let me press stop really quick, and then we'll be right back to it.